Okay, today we'll look at deformations in fluids, and what we are trying to do is come up with a way of relating stress to strain rate in a fluid. So, what one would call a constitutive law for fluids. What we are trying to do is trying to figure out, if I apply a force on the fluid, how does it deform, how does it flow? And you've already done a similar exercise in solid mechanics, in strength of materials, that is. So in solids, you said something like sigma is epsilon times E, where this is the strain, this is the stress, and this is the Young's modulus for the solid material. What you really did here was related the applied stress to the deformation in the solid, and the ratio of these was a property of the solid itself, of the material itself. So aluminum has a particular Young's modulus, steel has a different Young's modulus, and those values determine how much strain you would see, how much deformation you would see if you applied the same stress to let's say a cylindrical rod of a particular dimension. We are going to do the same thing here now for fluids. So what we are looking for is something very similar. We are trying to say if stress is proportional to strain, then what is that proportionality constant, so that I can replace this proportionality constant by an equal to sign. The only caveat is that now we don't have a strain, we have a strain rate, because fluids don't stop deforming. In a solid, I could apply a particular stress, wait until the solid reached an equilibrium deformation, and that would be my strain. That would be the actual elongation divided by the original dimensions of the object. That would give you a strain. In fluids, we know that as long as you apply shear stress, the fluid will keep deforming. So there is no strain. The strain can be infinite if you keep applying the stress. So what we really need is a strain rate, the rate at which the fluid deforms, and that's what we want to express as a function of the applied stress in terms of this quantity, and that is essentially the viscosity. So we have now a constitutive law for fluids where viscosity takes the role of Young's modulus in determining the proportionality of strain rate to applied stress. The next question is, how do you define stresses and strains? In a solid, we saw in the one-dimensional system that if I, let's say, took a bar and applied some pressure P, let's say this had an area A, I would have said sigma is P over A, and that is, let's say the length is L. I would have said that this stress equals the strain, which is delta L over L times E, right? And so this would be the strain in the, let's have a coordinate system. So this would be the strain in the x direction. But in order to conserve volume, there would also have been smaller contractions in the y direction and in the z direction. We often don't discuss that in elementary strength of materials courses, but really there are strains in all three directions, and as a result there are stresses in all three directions. So let's look a little more carefully at the various kinds of deformation. That a fluid element can experience. I should say fluid element can experience. And we'll revisit those, we'll visit those in detail. The reason we want to do all of this is because we ultimately want to plug this into some kind of stress equation, some kind of momentum equation where we know that we can extract velocities out of the equation. So if I could figure out my strain rates as a function of velocity, I could write down a momentum conservation equation where the applied stress is related to the velocity through the viscosity. And that will give me an equation that I can solve to get my velocities and pressures everywhere. And ultimately, that's what we're interested in as engineers, trying to figure out what forces the fluid might experience or exert on bodies immersed in it and so on. So, okay, so let's say I have a fluid element. Let's consider just a 2D element for now. And let's say it's looking rectangularish at time t0. I'm going to say that when I observe it an instant of time later, it's deformed into something like that. So that's at t0 plus delta t. And I'm going to break down all the possible deformations that could have occurred for it to go from this shape to that shape. And I'm going to express each of those as a kind of strain and sum those up so that my total deformation, my total strain is equal to the difference of these two shapes. So we're going to say that's equal to, the first is of course translation. So let's say it went from here to there. It just translated in x and y. So let's have another where it actually expanded. So it stayed in place, but the size increased. We'll call this, okay, so this is translation. This is what you might call dilatation. We have a third. This would just be rigid body rotation around some axis. And the fourth is pure shear deformation. So you can go from one shape to another in a time interval delta t by undergoing all these motions. Now what we want to do is express all of these motions. Let's say this is the initial dimension of the element. What we want to do is express each of these motions, each of these resulting shapes in terms of the velocity field so that I can express my strain rate, total strain rate as a function of velocity, then calculate the applied stresses through the viscosity. Okay, so in order to grab the change in volume due to the process of dilatation, what we are really looking for is, let me shade this. So we are looking for the increase in volume because there's a change in the u velocity here. So if the left-hand side is traveling at u and the right-hand side is traveling at u plus delta u, the relative velocity of this phase with respect to that phase is delta u. And so it traces out in time delta t an additional volume delta u times delta t. So if my original volume delta v is delta x, delta y, delta z, what I'm looking for is a delta delta v. That's the change in volume due to delta u, delta v, delta w at phases. So let's look at just the x direction for now. So if I ignored the v velocity and I just looked at the change in volume due to delta u, so delta u would trace out a delta delta v of delta u times delta t times delta, so this is delta x, delta y, so delta y times delta z, where delta z is in the third direction, we aren't really considering that. And this delta u I'm going to write as a partial derivative del u del x times delta x times delta t, delta y, delta z. And so my fractional change in volume, or the relative change, which is sort of like a strain rate, like what you would have in bulk when you looked at compressibility of a solid material, you look at the volume coefficient of expansion. This is sort of like that. So this turns out to be delta delta v x over delta v. So that gives me, I have a delta x, delta y, delta z on top and bottom. So that's delta u, well, del u del x times delta t. And so the rate of change of volume I'm going to call it a relative volume, that is d delta v by dt, where delta t tends to 0. And so that's a limit, and I get del u del x. And similarly for the y direction, I would get del v del y and del w del z. So my total rate of change of volume in all three directions would be the sum of the partial derivatives of the velocities in the three directions. And so I would get the dilatation strain rate So that takes care of dilatation. And the last thing we are going to look at is angular deformation, and that's the one that is the trickiest to follow through. You have to do some geometry there. So we are trying to figure out how something like this ends up as something like that. And the reason something like that might happen is because there are gradients in the x and y directions of velocity. So if I have my velocity components as u and v here, there might be a gradient in the u velocity in the y direction, so that here it's u plus del u del y, delta y, and similarly there are gradients of the v velocity in the x direction. So here I'll have v plus del v del x delta x. So if I were to mark these as, let's say, that's my point O, that's my point A, and that's point B. Well, OA might be rotating this way and OB might be rotating that way, or it might be expanding as well, depending on the velocity field in particular. So we are going to assume that counterclockwise rotation is positive. And what we want to do is get a relation between the velocities and the angular deformation, the rate at which OA is tracing out an angle. So let's say I have, I'm going to erase these arrows so that we can define angles. So here's my deformed shape. So I have an A prime, a B prime, and let's say this is delta beta, that's the angle, that is delta alpha, that's the angle again. Okay, so angular velocity of line OA by definition WOA is the limit as delta t tends to 0 of delta alpha by delta t. So that's the rate at which alpha is changing with respect to time. I take sufficiently small intervals in time. Because I'm looking at small intervals in time, delta alpha is approximately equal to tan delta alpha, and tan of the tangent of delta alpha is nothing but this distance over that distance. So if point O covers a velocity, has a velocity v, and A has a velocity v plus del v del x delta x, the relative velocity is just this term here, and that times delta t will be the vertical distance that A prime occupies relative to A. And so therefore WOA will be limit as delta t tends to 0 of del v del x delta x. That's the velocity times the distance times the time. So that's the distance in that direction divided by we are taking the tangent, so we need to divide by this distance, which is delta x, and we are taking the time rate, so we have a delta t as well, and so this whole thing ultimately becomes del v del x. And similarly, WOB, it's actually omega. So let me call this omega rather than W. Similarly, omega OB will be limit as delta t tends to 0 of delta beta over delta t, and that by a similar argument will become del u del y. So if delta, now that's the way I've drawn it, delta beta should be negative because counterclockwise is positive, so I'm just going to say that's minus del u del y. So if I look at the average rate of rotation, the average rate of rotation will just be half of del v del x minus del u del y, and I'm going to call this omega z because this is about the z direction where this is x and that is y. So this whole thing represents rotation in this plane, in the xy plane, about an axis passing, a z axis passing through here. I could do the same thing for rotation in the other two directions. So I could write average rates of angular deformation in the y and z directions. And if you notice the symmetry that we got with those expressions, it should be easy to write them down. So similarly, omega x would be half del w del y minus del v del z, and omega y would be half del w del x minus del u del z. I think I have this wrong. It's the negative of this. So that should be half del u del z minus del w del x. So I could define the rotation vector and so this would look something like now if I compare this with the curl, so you see that cyclic symmetry there. If you compare that with the curl, curl of a vector and curl of the velocity in particular, We know how that goes. This would be half of the determinant and so what you get is essentially these two turn out to be the same. So what we are saying is the rotation vector is nothing but half the curl of the velocity. Now often instead of using the rotation vector, we don't want that factor of half, so we just drop that and we call it a different name. So the vorticity, as we call it, is just twice of this. So we often use the vorticity omega is 2 omega, and so it's just curl of V.